So I'm just clicking go live now. You have 1 minute to think. Good luck.
Good evening, everyone, and welcome to another exciting session of Astronomy on Tap Leiden. And as you can see, that today it's going to be online, like the last few months, or actually almost about a year that we have been doing it. So today we have two really exciting talks that is going around some. What is it called, like extreme astronomy, you can say it. So we're gonna have some one talk about planet hunting from Antarctica, which is already sounding very extreme in terms of where it is being done. And then we're going to have another talk about the sound of spinning stars. So about the pulsation of stars like our sun and others. So yeah, it's very good to have you all with us today, and then I'll move on to our next slide. So for those of us who are new here today, welcome, and of course, welcome to everybody else who are joining us for more than once. For those who need a little reminder, Astronomy on Tap is an initiative that started in 2013. That's actually quite a number of years now. It started in New York City, and ever since then, it has been going on over 40 or 42 locations all over the world. And Astronomy on Tap Leiden is the first of its kind that started in Europe. And we usually meet the last Monday of every month. We meet on a local bar at Leiden, but now because of the current situation, we're doing it online. So actually, we started in March 2017, and that brings us that today, and this session is actually marks the 4-year anniversary of Astronomy on Tap Leiden. So thank you all for being with us, and thank you all who have been with us since the beginning, and or who joined us midway, who joined us now. It's all of you who are joining us that makes organizing this very rewarding for us. So yeah, and I suppose those of you who are joining us today, you're already finding us on YouTube, but we also have a website, and we are active on social media in Facebook, Twitter, and Instagram. So if you are there, please feel free to give a shout out and feel free to tag us there. We'd love to hear from you that you are joining us from different social media as well. And also in our social media, we give updates about when our next sessions are going to happen. But if you are not big on social media, you can also sign up for our newsletter in our email that's down below here. So we send out emails also twice a month max to just let you know about which are the next sessions that are coming up. So yeah, feel free to join us in any way that you like. And today we are streaming online, and you can communicate with us via the YouTube chat that you can see on the right side of the YouTube channel. So please let us know where you're watching from. Let us know that you're watching us, you're with us. Say hello. It's very nice to hear from you all, because we cannot, it's not an in-person thing that we're having now, but it's still very nice that because of online, we can actually connect to many people from around the world. So it's, yeah, it's very nice to hear from all of you. And apart from that, during the talks, when you'll be watching it, you can also leave your questions for the speakers in the live chat. So after each talk, somebody from us will be moderating the questions, and we'll be passing the questions to the speakers. So yeah, that way you can have them answered. So yeah, please feel free to ask questions. We'd love to hear from you. And before we go to the talks, we usually share some exciting news on astronomy every month. And this month on astronomy news is actually a very exciting thing, which is for the first time, astronomers have been able to measure the polarization, which is a signature of the magnetic fields around black hole. So this is actually the work of the Event Horizon Telescope team who published the first ever image of the shadow of a black hole, actually almost about 2 years ago from now, on April 2019. So putting on top of that work, now they studied the polarization, which is very exciting because it's the first time that it's been done. So yeah, very exciting time to be living. And without further ado, we go to the program for today. So tonight we're gonna have something a little different from our usual program. So we'll have two talks, one from Georgina Dransfield about the planet hunting from Antarctica, and then without our usual break or quiz, we'll just directly go to the second talk after a question answer session. So after each of the talks, you'll have, there'll be time where you'll have your questions answered. And afterwards, we'll have a closing remark, and this will be a quick, nice session. And we hope that you'll be with us throughout all of this. And for our first speaker today, we have Georgina Dransfield, who is a graduate student at the University of Birmingham. And before starting her PhD on the field of exoplanets, she taught in high school physics for over 6 years. And she left actually this very rewarding field of work for something super exciting, which is that when you think about your next destination for holidays, probably South Pole is not what you think about. But when it comes to looking for planets outside in the universe, this is about the coolest place on Earth that you can go to. And she does exactly that for her research. Apart from science, she loves winning at board games and just staring contests with her dog, Amy. And once she took her boyfriend all the way to Iceland to propose to him at 1 a.m. on a park bench using edible rings. This is exactly what you see here on the right from a tweet of her then boyfriend, who thankfully said yes, and now they are married. And today she's going to tell us more about her planet hunting from Antarctica. So without further ado, Georgina, I'll leave the screen to you.
Hi, so hopefully you can all see my screen okay now. So thank you very much for having me. So I am going to tell you a bit about planet hunting from Antarctica. Before I get started, I just have one very quick warning for everybody who's watching today. And that is that I live with this here ferocious beast called Amy, the dog that I have staring contests with. So she sometimes barks for absolutely no reason whatsoever. So if that does happen during this talk, I apologize in advance. So who am I? I'm George, and I used to be a physics teacher, as I just mentioned. So I would spend my days in my lab playing with lots of different kit, and I decided to turn that all in and instead go hunting for planets outside the solar system. Sometimes this involves traveling to really cool telescopes around the world and watching Love Island to keep myself awake during the long nights of observing. So I'm going to tell you a little bit about how I look for new planets outside the solar system. Now, you may have heard it said that everything we've learned about the universe has come from starlight. Until a couple of years ago, when gravitational waves were discovered, it was everything, but now it's just almost everything. And this is still very true as well for looking for planets. We have to contend with the fact that planets are really, really small and really dim when compared with their stars. So we can't actually see planets outside the solar system. Instead, what we do is we monitor the stars and we take measurements of their brightness over time. And of course, we plot graphs of this. So a graph that looks like this of brightness over time is called a light curve. And occasionally our light curves are a bit flat and there's nothing much to see there. But sometimes something does happen. Sometimes a planet passes in front of its star and it blocks out a tiny bit of its light. And this causes there to be a dip in the light curve, which we call a transit light curve. And the event where the planet passes in front of its star is called the transit. So these kinds of dips could be planets passing in front of their stars, but they could be something else. It's much more exciting if we monitor the star over a long time and we see that this event repeats over and over again, and it's always the same depth and it's always the same time apart. But you might be wondering now, how do we know where to look? Do we just point blindly at the sky and hope? Well, no, not really. That's the job of surveys. So surveys are missions that have the job of just staring at the sky blindly and looking for candidate planets. The first space survey was a mission called CORO. CORO stands for Convection, Rotation and Transit, and it was a little French space telescope that was originally intended to look for wobbly stars, which Ollie's going to tell you about later. But everything got really delayed, and then the first exoplanet got discovered and they were able to just tag that on there in the end. CORO discovered about 34 exoplanets, I think, so, you know, not bad. After that came Kepler. Kepler was an altogether different beast. So Kepler's mission, its prime mission, was to look for planets outside the solar system by looking for transits. Kepler's observing strategy was to just stare at a patch of sky, the same patch of sky for years. And using the transit method, Kepler found over 2,000 exoplanets. That's over half of all exoplanets known to date. They came from just Kepler. So we don't have Kepler anymore, but nowadays we have TESS giving us candidates. So TESS, that looks like this, stands for a Transiting Exoplanet Survey Satellite. It was launched in 2018 and its prime mission was meant to be 2 years, so it's already into its extended mission. Instead of looking at the same piece of sky all the time, it's decided to look at the whole sky, and it split the sky up into 26 sectors, and it stares at the sectors one at a time, 27 days each, and then once a month it sends us down some data and we look at the data and we see what's there. So far TESS has discovered 120 planets, and we've got about 1,500 planet candidates waiting to be confirmed. So a day in my life then looks a bit like this. This is a TESS light curve, and if I see a TESS light curve that looks like this and has a beautiful U-shaped dip in it, then, you know, maybe I get a bit excited and think it's a planet. But I remind myself that I have to calm down because it's not really anything at all until you see it happen a second time. And then if you see it happen a second time, then it's more exciting, but it still could be nothing. So you need to make sure that you can see this repeating over a long period of time. Something like this does look pretty promising because it's always the same depth and the spacing between the transits is pretty even. But you still need to hold the champagne because this could still end in heartbreak. The reason for that is eclipsing binaries. Now, it's not that I hate eclipsing binaries, but eclipsing binaries make my life really difficult a lot of the time. An eclipsing binary is two stars orbiting a common center of mass, and they sometimes eclipse each other, so they block out each other's light. The problem with eclipsing binaries is that their light curves mimic transit light curves. And this is especially a problem for TESS. If there is an eclipsing binary nearby or in the background, then its light can bleed into the light of the thing that you're looking at, and it can look like you found a transit. So this here shows you TESS pixels. Each of those squares is a TESS pixel, and all of those little dots are stars. And you can see how the light from different stars just bleeds into one another, and you're not entirely sure what you're looking at. So how do we figure out whether we're looking at an eclipsing binary pretending to be a planet just to make us sad, or if we're looking at a planet? So the magic happens with EXOFOP. EXOFOP is the Exoplanet Follow-up Observing Program for TESS. And what we do is we basically follow up on all the candidates that TESS produces, and we classify them as, you know, sometimes good candidates, sometimes confirmed planets, but a lot of the time not planets. So this is a big part of what I do. I follow up on TESS targets, and one of the telescopes I do that with is ASTEP. So ASTEP stands for Antarctic Search for Transiting Exoplanets, and ASTEP is beautiful. It's actually one of the coolest telescopes in the world, not just because it's in Antarctica and it's cold there, but it has some outstanding conditions for astronomy. The atmosphere is really thin. The stars don't do that annoying twinkling thing that makes it really hard for us to find planets. And it was originally meant to be a survey in its own right, but now it's doing follow-ups instead, which it's far better suited to. Now, ASTEP is one of the best telescopes to look for planets with TESS, and the reason requires for us to take a step back and ask ourselves why we're actually doing this in the first place. Why are we even bothering to look for planets outside the solar system? What is the ultimate goal? Well, the ultimate goal is that we want to find life outside the solar system. We want to find life anywhere in the universe, really. However highbrow people want to be, this is what we're after. And as far as we know, finding life requires finding liquid water. And we definitely know that finding liquid water means that we need to find planets that are not right up next to their stars getting completely fried. We can figure out how far away a planet is from its star by knowing how long a year is on that planet. And we know how long a year is because it's the time between transits. So it's the time it takes to go round its star once and get back to the position it was in when we first observed it. So we can figure out all of this. Now, here's the thing. Long years tends to mean long transits, and wanting to observe long transits is kind of a challenge. So if you ask your average Joe telescope to observe you a transit that happens once every 60 days, i.e. 6 times a year, and this transit, say, is 10 hours long, and if you're being really, really optimistic and you say that average nights are about 10 hours long, so you're then just going to throw all these numbers into your maths box, and you're going to try and figure out if this is likely that you'll be able to observe this. And most of the time, the answer is just going to be a no. So you might wonder why 10 hours is not the average night for us. And for that, we need to think about when is it good enough to actually observe. So you might think of a nighttime starting when the sun sets, but that just means that the sun has crossed the horizon. This is not yet good enough for us to observe. We need the sun to be further down than that. So if it's 6 degrees below the horizon, we say we're into civilian twilight. Nautical twilight is the minimum usually required to start astronomical observations, but some telescopes require astronomical twilight too. We tend to observe an ASTEP between nautical and civilian twilight. And just to think about like what nights look like typically on your average telescope, this is what nights look like from Paranal in Chile, which is a really popular site for observing. There are loads of telescopes there, and you can see the dark bands in the winter, show you when the longest nights are happening. So those nights are not particularly long. But if you look at the nights on ASTEP, well, we have one really funky night because the sun will set and we will start to have twilight on the 25th of May, and then it will remain twilight until the 19th of July. So we get one night that lasts 2 months. So, observing long transits that don't happen very frequently, that's kind of our thing. And that led to an observation of this here candidate. So this candidate that TESS provided is called TOI 282b. TOI stands for TESS Object of Interest. And we were able to observe this transit that nobody else could catch. It's over 10 hours long, and it only happens once every 56 days. And because we were able to observe this planet repeatedly when no one else could, I'm now preparing a paper to announce the discovery of this system. And the system actually has 2 planets, not just one. So what does this system look like? Well, we've got 2 planets, TOI 282b and TOI 282c, great names. We know that both of them are similar in size to Neptune, and they have pretty long years for exoplanets, 56 days and 84 days. And given their densities, we're going to classify these as gas giants. You can see there, those temperatures are pretty high. So, still can't sustain liquid water unless you do like your oceans boiled. So maybe not habitable. But that doesn't mean we don't care about these. You might be wondering, if the thing that we're trying to do is find life, why do we even care about planets that aren't habitable? Well, we still want to know. And the reason is this: if you think about the solar system and the kinds of planets we have here, we've got a bunch of rocky small planets close to the sun, and then we've got some gas giants further out. The planets that I've found are like Neptune, gas giants and, big, but they are closer to their star than Mercury is to the sun. And their star is hotter and bigger than the sun. These planets are actually really common 40% of the planets that we found in the solar system, in exoplanets, are warm Neptunes that are really close to their stars. But we don't have anything like this in the solar system. And that's kind of odd. It makes us think that maybe the solar system is special after all. We also don't know how these planets can form. So, there's a lot to learn about whether the solar system is an interesting, unique place or not, and also about planet formation just by cataloging these different kinds of planets. So the plan for the remainder of the observing system for me then is to keep doing this. So we found ASTEP's niche, which is long transits that nobody else can observe. And we've got about 25 of them that we're going to be following throughout the observing system. And we're hoping that we'll be able to confirm a bunch of new planets. So that's pretty much what I do. Now, before I go, I just want to leave you with one final thought. So the eagle-eyed among you might have noticed that I have been in the top right corner counting acronyms, and there have been 5 acronyms so far in this talk. I tried to avoid them, but they're just inevitable in astronomy because astronomers really like acronyms. So here are some examples of some absolutely brilliant acronyms that I've seen in papers just in the last month. Speculus that you see there is actually a project that I work on as well, and I'm a really big fan of that acronym. It's beautiful. Now, this observing program of looking at long period, long transit planets, I would really love to name it and have an acronym all of my own. And I did try, but it turns out I'm maybe not a good astronomer because I can't come up with an acronym for my program. So I tried, for example, taking inspiration from this recent paper, and they named their observing program TIME, which I thought was really cool. So I had a crack at making oregano fit in there instead, but that doesn't really work. So I'm going to have to scrap that one. I also tried taking inspiration from the brilliant Laura Kreidberg, who named her software package Batman. And I thought maybe I could also go with Justice League theme and call it Flash, but the H doesn't really fit in there either. So my ask then to people watching at home is, if you think you're better at acronyms than I am and you can help and you would like to be immortalized in the acknowledgement section of my upcoming paper, then please head to www.hiitsgeorge.uk and send me your ideas. On that website, you will find multiple pictures of my dog and a little contact form to send me acronym ideas and nothing else. So thank you very much everyone for listening, and here's one final picture of my dog, and that's me out.
Great, thank you so much, Georgina. This was a very entertaining talk and I loved your animations.
Thank you.
So we already have some questions in. The first question is from Andrew from New Zealand. Quite a long way. Would a star brown dwarf binary system be recognizable as not a planet?
Oh, that's a really good question, actually. So Speculus, which is the other mission that I work on. So when they saw first light on their telescopes, the first thing they found was a brown dwarf eclipsing binary system, and it was like incredibly rare. So these are difficult to distinguish because, so people who don't know, brown dwarfs are kind of failed stars. So they never actually managed to ignite, and they have sizes and temperatures that are comparable to the biggest exoplanets that we know of, called hot Jupiters. And the line between them is actually really blurred. So the answer is, I'm not entirely sure. I think that we'd probably be able to figure it out eventually if we can take spectroscopic measurements of the secondary, so the thing that's orbiting the bigger thing in the middle, and then we can figure out if that looks like it's producing its own light or if it looks like it's just a ball of gas that's orbiting something else. So that's a really good question.
All right, great, thanks. Then the next question is from Wim. How do you know the density of TOI 282b and c?
Oh, that's another great question. So we know their sizes because of the depths of the transits. So the depth of the transit basically tells us the percentage of the star's light that's being blocked out. And if we know the star's size, then we can use that to figure out the planet size. And then finding masses, well, that's a challenge. There's 2 ways that you can get masses for planets. One of them is by taking radial velocity measurements. And this basically involves thinking about how when you have a planet orbiting a star, because of its gravity, it actually makes the star wobble a little bit on its orbit. So it's not just spinning, but it's doing a little bit of a wobble. So we can measure how much of an effect the planet's having on the star, and that gives us a mass measurement. In the case of TOI 282b and c, they're a very special system because the planets are in what we call a resonance, which means that the orbital periods are a nice multiple of each other. So the multiple there is they're in a 3:2 resonance. So 56 days is 2 times 28 and 84 days is 3 times 28. And these systems are really special, and it causes the transits to sometimes be a little bit late and a little bit early. So by taking really precise measurements of how late or early the transits arrive, we can use that with some really complex simulations that I don't do, somebody else does for me, to figure out the masses of the planets. And then from there, we can calculate the densities.
Perfect, thanks. Then our next question is from Chris. Could you detect a planet of a similar size and period to Earth?
Oh, so right now, if it's orbiting a star like the sun, no. So this is one of the challenges. So we don't know at this moment in time if the solar system is actually special and there aren't planets like Earth that close and that small, or if it's just that we don't have good enough instruments yet to find them. So Earth would have a transit depth on a star like the sun of something like 0.008%, which we are not capable of detecting. We can find Earth-sized planets if they are orbiting really cool stars. So that's what Speculus does. They're looking for terrestrial type planets orbiting a type of star called ultra cool stars. So these could be brown dwarfs or just very, very cool actual stars. But yeah, around the sun, we can't do that yet.
Hopefully in the near future.
Oh yeah, hopefully. So, I mean, we would really need to improve the precision of our instruments for measuring light, because the problem is that when you take measurements like that to get a light curve, you have a bunch of noise. So on the real test light curves that I showed you, you would have seen there were some error bars that kind of show you where that measurement could fall between. And when you have a really, really shallow transit in your light curve, it's hard to distinguish it from the noise. So we'd need to improve the precision of those instruments. But, you know, hopefully, I mean, 15 years ago, we never would have been able to detect planets as small as TOI 282b and c. So we've already come a long way.
Yeah, definitely. Then we have another question from Tuan. Does a sister telescope to ASTEP for the North Pole exist, or is there one planned?
Oh, so there isn't one, and there isn't one planned at the minute, actually, but that would be a really cool idea. I don't know what photometric conditions, so photometry is measuring light. So I don't know what the conditions for that would be like in the North Pole and if the atmosphere is as stable. So in Antarctica, it's not just the fact that it's really cold and we get the polar night, but also the fact the atmosphere is so thin, and there are these domes, which are areas that have kind of very high altitude. So that makes the atmosphere be very thin. And I don't actually know what the geography is like close to the North Pole and if that would be the case as well. So you need that kind of combination of great things so that you can have those great conditions for observing.
All right, thank you. Let's do one more question from Shetan. As you said that this transit was detected only by ASTEP, how do we follow up for this like we do for TESS? And if we do not follow up for these, then why so?
So that's a really good question. So TESS has a bunch of issues that means that you can't confirm a planet just with TESS. So for example, the issue of the pixels being so big. So with ground-based follow-up, our precision is much higher and we can detect whether the event is on target or not. So our I don't want to use that word. So the opening that we look at, we can make a light curve for every single star individually within that small field of view, and we can confirm that the event that we're observing is not happening on any of the other stars. So if it was a background eclipsing binary, then from the ground we'd be able to see the individual stars, and if we made a light curve, what we'd see is a much deeper event happening at the same time, and because it's blended, it would look shallow on the star that we're observing. So by observing from the ground with a good enough telescope like ASTEP, you can confirm that the event is on target. So that already rules it out. Generally, if it was a single planet, you also would need a mass measurement to confirm it's a planet. Because there's another binary scenario that could still be a binary and not a planet. But because this has two planets and they're in a resonance, it means that the statistical probability of this being a false positive, i.e. being a binary pretending to be a planet, is so close to zero so as to be, just impossible. So that allows us to validate planets without taking direct mass measurements.
All right, there's actually one more question for you, if that's okay.
Yeah, sure.
From Ruslan, what is the fraction of exoplanets that we are missing out of due to the projection effect, such as a phase-on view where the planet does not pass in front of the star?
So that's actually a really good question. I'm not entirely sure. So I don't know actually what the percentage is. I know that someone has a lot of people have calculated occurrence rate, so how frequent they think planets are and how many stars they think would have planets. And I think they found that solar-like stars, so stars like the sun, on average should have at least one planet. And I'm guessing that we'll be able to get better statistics for kind of how many we're missing out on by not having the right angle once we've got more of them, but I'm not entirely sure what the proportion is. Sorry.
All right, then a big thanks again. I'll applause for everyone here. And then we're gonna go back to Lemon.
Thank you. I'll just quickly share the screen again. Yeah. So thank you, Anik, for doing the question answer session, and thanks, Georgina, for such a wonderful talk. And I hope the audience have enjoyed the talk and the discussions afterwards as much as I did. So as I said before, our today's program is a little different than our usual one, and without taking a break, we'll now quickly go to our second talk of the day, which is going to be from Oliver Hall about the sound of spinning stars. Before starting the talk, a little bit about our speaker. So Oliver Hall, he is in his first year as a research fellow in the European Space Agency, or ESA, in the Netherlands right now. And he started here recently after finishing his PhD from the University of Birmingham, where he studied astroseismology. This very cool sounding term is the study of variable stars. And specifically, he studies how we can use big amount of data about these variable stars to understand more about the physics behind them. By variable stars, we mean stars that change their brightness in different time frames. So they're faint and bright and so on. So I'm sure he'll tell us more about that. And when he's not doing his science, he enjoys games, exploring Leiden, and wrestling his puppy. And one fun fact about him is that he is a German-British dual national, and he was born in Hong Kong. And since the age of 5, he has been traveling between UK and Netherlands already 3 times. And according to himself, he will make a terrible homing pigeon. But today he's going to tell us more about, he's going to give us an introduction to how stars make music and how we can use this music to understand the stars a bit more. So Oliver, the stage is yours.
All right. Cool. Okay, I hope you can all see that all right. I can't see the Zoom window anymore, so I'm just going to go ahead and hope things go well. Thanks for having me, first and foremost. My name is Oliver, and today I'm going to talk to you about astroseismology, which is a fancy sounding word, but really just means listening to stars, or looking at how their brightness changes. And it's always good to follow this on from a talk about exoplanets, Because one of the ways we understand exoplanets is by understanding their star really well. And one of the ways to understand the star really well is by using astroseismology, by listening to the star and seeing what it tells us. So I'm going to take you on a bit of a journey through the interior of stars, and it involves some sounds and loud noises. So just be warned, and I'll let you know before they show up. So there is a lot going on inside stars. This is a picture of the sun taken from space. And already on the surface of this, you can see that there's loads and loads of small details. There's big flares and there's magnetic loops in the top right corner carrying material into the air, and there's areas that are more active and less active. And there's loads of stuff going on inside the star as well. Stars like the sun, but all stars are huge balls of gas, mostly hydrogen. And this gas is all it's all plasma. The electrons are flying around. It's really hot material, and it's constantly in motion. And this motion changes depending on where in the star you're looking. In the very center of the star, we have the core. That's this little blue region on this diagram. And in the core, hydrogen atoms are combined, they're fused to form helium atoms. And with this fusion, a load of energy is released. This energy leaves the core, and then it then moves into the dense radiative region. That's this yellow area around the core. And the radiative region is so dense that it takes the energy produced in the core. This comes in the form of light. It takes this light so long to leave the star. It's in there for about 1 million years in the radiative region because it's so dense and it just takes a long time to travel through. And the way you can imagine this kind of as heat traveling through a hot pan that you touch, right? The pan has been heated up and it travels through the metal, and the metal's really dense. Now, after its million-year trek through the star, the light will eventually reach the less dense outer regions. And when we reach this less dense outer region, the manner in which the heat is transported, the light is transported, changes. Now we've reached the convection zone. And in the convection zone, the way it works is that the material close to the radiative zone is heated, and this hot material rises, right? This is a gas, so it behaves the way that we expect gases to work. This is the same as your radiator in your living room. The radiator will heat the air around the radiator, and that heat will then carry the air up to the ceiling where it will lose the heat, and then the air will sink back down again. And the same thing happens in a star. The hot regions rise up to the top, and then they deposit their light and energy into the universe when it eventually arrives on Earth. And then the material, having lost its energy, will sink back down inside the star. And this is happening constantly. So if you look at the surface of the star using a space-based observatory, such as the ESA Solar Orbiter mission, it looks like this. So this massive grid pattern of little dots are loads and loads of granulation cells. These are pockets of material that are lifting light up to the surface and then falling back after they've cooled. And each one of these little circles is the size of North America for scale. And if we zoom in on this, this is a video taken by the David K. Inouye telescope in Hawaii. You can see that these things are constantly in motion. This happens over the course of many hours. So these bright regions are where lots of light is being deposited. This is the hot material. And then the dark regions are where the material is cool and it's sinking back into the star. So you can see this is constantly in motion. There's heat being thrown out into the universe, and then the material is cool and moving back in. And it's going to sink all the way back down to the radiative region where it will soak up more heat and then move back up to the top. So at any given moment, a star like the sun is constantly in flux. There's stuff moving around the outside of the star all the time, and it's just really turbulent and chaotic, you know, like kind of a windy storm or a turbulent ocean. And because this motion is happening on the outside of the star at all times, there's also loads of stuff happening inside the star, because every time a granulation cell moves around a little bit and disturbs the stellar material, it sends kind of a shockwave traveling through the star. And this shockwave will travel through the star and interact with the shockwaves that come from other bits of the star. And all these things will interact with one another. So you can imagine if there's a little shockwave in the top left corner, it will travel through the star. Maybe one crest of the wave will go right through the middle and one will deviate off a little bit to the side. And then when they reach the opposite side of the star, they reach the universe, the vacuum, and they don't want to go there. So they reflect and move back into the star. And the one that's gone a little bit at an angle curves when you reach the really dense interior, because it's so dense, it kind of doesn't want to go there either. So it kind of moves out of the way. And so you have these motions that these waves take through the star, and they kind of form different shapes. They go in different directions and they'll begin interfering with one another. And when they interfere with one another constructively, so that's when a wave finds another wave that it likes and it builds on top of itself, it creates standing waves. it creates these motions, these oscillations, this kind of in and out motion inside the whole star that is supported and is supported continuously and is happening continuously. So on the right, I'm showing you the two types of motion, which are greatly exaggerated, that the star will be undergoing, that are related to waves that have traveled this kind of way through the star. So on the top right, I'm showing you the radial oscillation. We kind of call this like a breathing oscillation of the star. This is due to waves that are traveling through the center of the star and then reflecting, going back through the center. So this is just the star expanding and getting brighter and contracting and getting less bright. And when you have waves that take less conventional routes and that curve off around the middle, you get something like the one on the bottom right, where you have 1/4 of the star in the top, which will be expanding, and then the region next to it will be contracting, and this will all be happening throughout the star. I can't do it with my hands, obviously, because there's too many different points going in and out. But you get these really interesting looking motions. And as again, this is really exaggerated. Stars obviously mostly still look round, but the surface is changing ever so slightly, and we can measure this, as I'll show you in a bit. And of course, it's not just the surface of the star that's changing. The inside of the star is also constantly in motion, because these waves are traveling through the star. So inside the star, stuff is being contracted and it's being expanded again. And so the whole star is in motion together. And this is the thing that makes astroseismology really interesting, because these waves don't just occur on the surface. They're traveling through the entire star, but they give an effect that we see on the surface. So this means that just by looking at the surface of the star, we can understand what's happening inside the star all the way down to the very deepest interior in the core, because the waves are traveling through the star and they're affected by everything that they meet along the way. Do they meet a denser region? That affects them. Do they meet a region where the sound speed suddenly changes? That affects them too. So by looking just at the surface, we can understand what's going on inside the star. So because of this, in the field, we like to think about stars as musical instruments. Imagine you have a star like the sun, as you can imagine it like a saxophone. The convective region on the outside, which is turbulent and in motion, you can imagine that like somebody blowing on the saxophone. And then the insides of the star is like the saxophone itself. It has specific notes and specific frequencies at which it vibrates. And the same thing's true for the saxophone. If you blow into a saxophone, it will make specific noises, because this depends on the size of the instrument and the way it's been designed. And so this analogy extends a little bit further as well, because if a sun is like a saxophone, well then a smaller star is maybe like a piccolo, like a red dwarf, a little star, a cool star, that will have oscillations and frequencies which are a higher pitch, that oscillates more often than the sun does. So for reference, the sun expands and contracts every 5 minutes or so. And for a really small star, this will be on the order of maybe 1 minute or maybe even less. So this is the same as a small instrument. And then for a really, really large star, an evolved star like a red giant, these things are huge, 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 much huger than I'm showing here. This isn't really for scale. You can imagine that as a tuba. This is a really low pitch instrument. And because the star is so big, it makes a really low pitch sound. So by listening to the stars, we can already know something about what the star is like, because if you hear a tune from a wind instrument, you will know whether or not it's a tuba or a piccolo. Those things sound completely different. And this also depends on the contents of the star. For example, if you sing a note right now, but then breathe in a bunch of helium and sing the note again, the sound will be different, right? And so the vibrations of the star, the sound that travels through the star, sounds different as well, depending on the contents of the star. Is it a newer, more recent star that has more atoms in it that aren't just hydrogen or helium? Or has this star evolved quite a bit? Has it burnt a lot of the hydrogen and converted it into helium in the core? That might change the sound a little bit as well. So we can use this to find out the age of the star. So we like to use this instrument analogy, but in practice, as we'll see in a moment, it's really not like the stars are playing you a beautiful symphony. You can imagine it more like somebody slamming their hands on a piano and playing all the notes at the same time, or as I like to think of them for comedic effect, it's as if the star is screaming into the void. Now, of course, if you imagine a star screaming, we don't actually hear the sun screaming at us in the daytime. And this is because famously in space, no one can hear you scream, because space is a vacuum and sound doesn't travel through it. So we can't actually hear the sounds in practice. What we're doing is we look at the surface of the star, and from the change in brightness, we can infer how they're vibrating. So for example, this is that breathing oscillation I showed you earlier. When it contracts, the star gets a little bit redder, it gets a little bit fainter because it is smaller. And when the star expands, it gets a little bit brighter. And so if we look at the star over time, we will see it get brighter and less bright. And we do this using space-based missions. So these are the ones, like George said earlier, we use the same missions that look at exoplanets, which is really useful, because by studying one star, we can both look at their oscillations and find planets at the same time. So this is great. We use a lot of the same data, George and I. So the first mission to do so was the Cora mission, which measured it for a couple of tens of stars, measured these oscillations for a couple of tens of stars. And then just like with exoplanets, Kepler blew the field wide open and measured these kinds of oscillations in hundreds of stars like the sun, and what we call the main sequence, stars in the main part of their lifetime, and in hundreds and thousands of evolved red giant stars, which it's easier to measure these kind of oscillations because they're so bright. Now Kepler and Cora both died and passed on, rest in peace. But now the new flag bearer of astroseismology, as well as exoplanet hunting missions, is the TESS mission, which studies areas around the whole sky. And this means that we're soon, hopefully, going to get lots of new astroseismic data for way more stars than was previously possible. So, as I said, when we use these missions to look at stars, it's the same way that we look at an exoplanet, right? So we measure the flux, the brightness of the star over time. And so if you point one of these telescopes at a star for a long time and you collect all the light that comes in, it looks something like this. So this is data, 3 months of data from a star called 16 Sig A. 16 Sig A, I believe, does have a planet around it, but it's not visible in these data. So there is no transits or anything going on. You just have this lots of this up and down noise kind of scatter. You might look at this and say, this is useless data. There's nothing here. It's just noise. However, inside this noise, there is actually the oscillations of the star. All these tiny up and down motions, this spread is caused due to the star vibrating, expanding and contracting, but also doing all these other little motions, like doing this kind of shape, you know, where the hemispheres contract and expand alternatively, and more complicated shapes as well. And so what we do to study these oscillations, if we don't look at this messy and noisy data, this doesn't tell us anything, but we do something called a Fourier transform. And a Fourier transform is a mathematical operation. People use it in the music industry as well. If you take something like this, flux over time, and you perform a Fourier transform on it, then it tells you what frequencies, so what frequency waves are showing up in your data. And we get something that looks like this. This is a power frequency diagram. So these peaks correspond to waves of different frequencies, so oscillations of the star that are showing up in the flux data. And then the different peak heights corresponds to how strong that oscillation is. So in this star, 16 Sig A, there is a really strong oscillation that occurs in the middle, and then the ones around it are a bit weaker. And this one in the middle corresponds to about 2 minutes for 16 Sig A. It's about 5 minutes for the sun. And because people smarter than me have modeled how stars work, and they understand really well how these oscillations happen, and they can model exactly what frequency the oscillations are supposed to happen at for stars of different sizes, we know what these different things correspond to. So you can see that there's this really nice repeating pattern of the kind of pairs with a little one and then a slightly larger one. And these correspond to the breathing mode, the expansion and the contraction of the star. And they keep repeating because these are different harmonics of the same oscillation. So the star will be contracting and expanding, but it'll be doing this at loads and loads of different frequencies. And we'll be measuring these all at the same time. So now, using these data, we can kind of get an impression of what a star sounds like. We can't really hear a star. I mean, for this is a frequency of 2 minutes, and the human ear just can't hear pitches that are that low. But we can take these data and we can scale them up, and we can kind of create an impression of what that would sound like for us. So I'm going to play what this star, would sound like to us now, which sounds kind of like crickets. We've got all these different overlaying sounds on top of one another, and it sounds kind of like a reasonable pitch, sounds nice to us. And now I'm going to show you, scaled up in the same way, what a red giant star sounds like. Which is much, much lower, and red giant stars oscillate at a much lower frequency. So this, using these data, we can measure things like the star's mass and the star's radius, which are really useful for when you're studying exoplanets, for example. But the thing that I'm specifically interested in is the rotation of stars. So everything we just discussed is the case for stars that are standing still. They're not moving, they're just standing there and oscillating and doing their thing, but they're not spinning around. But in practice, every single star is spinning around all the time. When they're born, they spin really fast. And then as they grow older, they lose some of that energy and they spin more and more slowly. So as stars get older, they spin more slowly. And I'm interested in finding out exactly how slowly they spin as they grow older. And the way I like to do this is by measuring their rotation using astroseismology. So we can explain really quickly how this happens and why stars sound different when they're rotating using a phenomenon that we're all fairly familiar with on Earth. And that's the Doppler effect. That's the effect of a car horn or an ambulance sounding different when it's coming towards you as to when it's driving away. So I'm going to give a little example of this in this video. This is a very loud car horn. So if that upsets you, as it does me a little bit, please just turn off your sound for a minute. So what's happening here is that as the car drives towards us, the car gives the sound a little kick. It kind of pushes the sound together and that makes it sound higher pitched to us. When the car is in front of us, it sounds the way the horn normally sounds, as if the car wasn't moving at all. And then when the car is driving away from us, it's kind of dragging the sound behind it and stretching it out until it sounds at a lower pitch. And the same thing happens inside a star. Because the star is rotating, waves that travel in the direction of the rotation will be stretched out and given a kick. And sounds that travel in the opposite direction will be, when they travel with the star, they'll be pushed together and given a kick. And when they travel in the opposite direction, they'll be stretched out. And the waves that travel up and down the star, and so aren't fussed about the rotation at all, they don't even know they're rotating, those are unchanged. That's like the star being in front of us. So we can imagine this like three cars on a roundabout, right? We have the car at the top traveling towards us. We are the ear in this scenario. We have a car in the middle standing still. And we have a car at the bottom, which will be driving away from us. And if we were to just listen to these cars that are all stationary, it would sound like this, which is the horn as it sounds for a stationary car. Now, if these cars are moving, the one coming towards us will sound at a higher pitch. The one in the middle will sound as we expected it to sound, which is normal. And then the car driving away from us will sound at a lower pitch. And so now if we put all these in motion, we will hear all three of these at the same time. So where before we only heard one sound, now, because the cars are rotating, we hear three sounds. This sounds pretty nasty, so fair warning. So this sounds distinctly different. And it's the same thing in a star. Stars that are rotating sound distinctly different from stars that are not rotating. So to just illustrate this using a nicer sound, I'm going to play you the sound of just one, corresponding to just one oscillation of a subgiant star. Stars a little bit larger than the sun, but a little bit smaller than a red giant. And then I'm going to play that sound again, but for a star that is speeding faster and faster and faster. And you can listen to how it changes. So that's the star not rotating. And now this is the star rotating faster and faster and faster. And so you can hear that as the star rotates faster, the sound, the effect changes more and more as well. And this is because the faster the star is spinning, the more of a kick it's giving to the waves that are traveling with it, and the more it's pulling apart the waves that are traveling in the opposite direction. So stars that are spinning really, really fast are relatively easy for us to measure the rotation for using astroseismology. So finally, just before we close off, why do we care about this? The reason I care about it is that measuring rotation using astroseismology is a kind of rare thing. We can only do this for the stars that have been observed using the absolutely best data from the Kepler telescope. We can't do this for any stars that have been observed with TESS yet. And so this creates a really unique data set because we're not just measuring something happen. We're not measuring some kind of superficial measurement of rotation for these stars. We are measuring a fundamental property of the star because by looking at the surface, we're understanding what is happening inside the star. And this tells us about what is happening inside the star, and this tells us about the evolution of the star. So the work I do specifically, I said I was looking at these stars to see how slowly they rotate as they age. And in a recent work which is being published this month, finally, we found out that actually older stars, like the sun, spin much faster than we expect. They actually, at one point, stop slowing down and keep spinning at a much faster rate until they eventually run out of hydrogen in their core and die of old age. So if there's one message I would like to leave you with at the end of this talk, is that next time you look up into the night sky, don't think of the stars as just stationary things which planets move in front of. Think of them as playing music to you, or if it suits you, as if they are screaming into the void, only heard by astronomers. Thank you.
Thanks a lot, Oliver. Great talk, and thanks for letting us listen to the universe. We already have our first question from Andrew. Would a planetary system affect the star's vibrations? And if so, would it be detectable?
That's a great question. So in principle, yes, this does happen. And this will happen if you have a really big planet, for example, a hot Jupiter that orbits really close in. I don't know if it's been observed. I do know that people have written models that describe how the oscillations change if there is a planet that is massive enough and close enough to the star to disrupt the oscillations. But I don't know if it's been observed. I'm assuming that it has because they've written models for it, and I've heard of it more than once, but I can't make that a promise, unfortunately. But if you give it a Google, it might show up.
All right, thanks. I think people are probably still writing up their questions. So in the meantime, I'll ask you my question. So I was wondering if dead stars also have these oscillations, such as white dwarfs?
Yeah, that's a really, really good question. So the whole thing I've described to you in this talk is just oscillations that are formed due to the granulation in the outer layers of the star, right? So small stars like red dwarfs, stars like the sun, and evolved stars like red giants all have outer layers where they have this convective motion of the material rising up and then falling down. Stars in the main part of their lifetime, but that are much hotter than the sun, will have different layouts, and they'll oscillate in different ways. So all kinds of stars oscillate, but they use different mechanisms that aren't like the one I described to you today. Even white dwarfs, dead stars, they also still oscillate due to the heat that's being transported from the inside of the star, which is still fairly hot, to the outside. That still causes motion that creates sounds that people can measure.
Cool, thanks. Maybe next time you can let us hear how that sounds like.
I'd like to. I haven't heard that myself, but I would like to hear that. Yeah.
Cool. Then the next question is from Fergus. Great talk, Oliver. I was wondering how much does the frequency change between each side of the spinning star, like the sun? That's
a good question. So let's see how I'll see if I remember this off the top of my head. This is on the order of a couple of microhertz. So I can't in my head convert that to something that's that happens on the order of days. But a hertz is one. If something is oscillating at 1 hertz, that means that it's doing 1 oscillation in a second. So a microhertz is much slower than that. So for example, yeah, the sun does 1 oscillation every 5 minutes, and that 5-minute oscillation in the sun corresponds to about 3,000 microhertz. But the changes due to the rotation is only 1 or 2 microhertz. So this is just a change in the seconds of the frequency, or less than seconds. So it's a really small change. This is why we can only measure it using these stars that have been observed using telescopes like Kepler for a really long time.
All right, next question is from Shetan. What would the effect of the inclination of the star's rotational axis with respect to us, the viewers and listeners?
Oh, that's an awesome question. I like that one a lot. I actually have there's a really good animation that I didn't include in this presentation that explains this. But in principle, yeah, so if imagine we're looking at this star that's on the slide here, and we're looking at it as if the axis at which it rotates is perpendicular to us. So the left side of the star will move towards us and the right side of the star will move away from us. And so the left side of the star moving towards us will have a really strong effect on what we hear. And the one moving away from us will also have a really strong effect on what we hear. Now, imagine that you turn this star by 90 degrees, so we are looking at the pole. When we're looking at the pole, the effect of the rotation actually stops existing to us. We can't tell whether or not the left-hand side of the star is moving towards us or not. It's just all spinning around, right? So if we're looking at a star pole on, then we can't tell whether or not the star is rotating. And this is actually a bit of a nuisance for us because there is no difference between a non-rotating star and a star that is viewed pole on. So if a star has a what we call a high inclination angle, so that the axis of rotation is not pole on but far away from us, then we can measure rotation more easily. Basically, it's something we have to take into consideration when we're trying to measure distant stars.
Okay, next question is from Chris. Can you tell the angle of rotation EA viewed from the pole, presumably no Doppler effect?
Yes, yeah, that's right. So if we view it from the pole, then there's no Doppler effect and we just can't tell at all.
Then we have another question from No Real Roots. Great talk. Could you envision a circumstance where the redshift and the blue shift cancel out, thus making it impossible to tell the star spinning?
Very good question. In principle, no. So I think I could move. I could probably go back a little bit to the slide where you can see. Let's see this one, yeah, where you can see these oscillations of the star. So for example, let's take this one in the middle, this really strong one. If the star was rotating really quickly, this would split into 3 distinct peaks. So one of them goes to a lower frequency and one of them goes to a higher frequency. And the shape that this creates in these data is unique. There's no way to mistake it for something else, basically. So if a star is rotating fast enough to cause this splitting, where we see 3 different frequencies, where we hear 3 different sounds, if it is strong enough for us to be able to hear this difference, then there's no way to mistake it for something else, basically.
All right, and then we have a final question from Ruslan. It might be quite difficult to separate all of the seismic motions. Do people run any simulations to model which sound is produced by which motion, or do we learn it just from observations?
No, absolutely. There is a huge and rich history of modeling astroseismic stars. And this is because people have known about the concept of astroseismology for absolutely ages. People can measure it in the sun, for example, but it's just been outstanding on other stars because, as George has said, you can't look at a star for a really long period of time on Earth because the sun gets in the way. So people have been modeling these stars for ages and have already had a really good understanding of exactly how they work and how the different oscillation frequencies show up on the surface before we were ever observing data like this. So when we finally made these observations, we could match it to the models really quickly and then really quickly begin improving the models. So for the last 15 or 20 years or so, there's been a real cascade of improvements in both the observations and the modeling side at the same time.
Okay, I think that was it. Thank you so much, Oliver. Also, applause from me again, and also a big thank you from everyone in the chat.
Thank you, Annick. And with that, we come to the end of our today's session. I hope, and I think we all hope that you all enjoyed the talks. It's very interesting to talks as much as we all did, and the discussions as well. And I hope all of your questions are answered. But if you still have questions, you can leave it at the chat. Actually, we can try to communicate it with the speakers later if you have some questions that you still didn't get answered. But and also, if you enjoyed this session and would like to check out more of such events, please go to astronomyontap.org and you can find information about other astronomy on taps that are happening in different parts of the world now, but online. And with that, our next event is going to happen on 26th of April. That's the last Monday of April in 2021. And more updates about this event is going to come in our social media channels. So please keep an eye on that. And also, as a reminder, if you don't do social media, please sign up with our email subscription and we'll send you an update when they're available. And with that, we'd like to thank again to our wonderful speakers, George and Oliver. Thank you very much for these very engaging talks. And in a normal circumstance, we'd like to give you these thank you tokens in person, which we couldn't do this time, but we'll make sure that they find their way to you, hopefully soon. And yeah, and Last but not the least, a big thank you to our entire team. It's a lot of work to put this work online, and it would never be possible without all of your constant efforts. And yeah, and thank you to our audience once again. And we hope you have a wonderful evening and good